Hello, everyone. I'm Marcio Carvalho. I'm going to discuss some of the work we've been doing at PUC in Rio de Janeiro in the area of microscale physics of oil displacement. So it's well known that when you're producing oil from reservoirs, you usually inject a water phase through injector wells. This water will push the oil towards the producing well. The amount of volume of oil that you are able to produce is a function of two main phenomena. One is how well the water is able to sweep the reservoir. So this is a macroscopic phenomenon. It's associated with the stability of this displacement front between the water and the oil. And the second important factor is how well the oil is displaced in the pore scale. So in the areas at which the water was able to achieve, how well was this pore scale displacement of the oil. So that's going to be the focus of our discussion today. And every enhanced oil recovery method try to attack or try to act in one of these two main physical phenomena and ideally work on both of them at the same time. So in terms of the microscale flow, if you're in the region of the reservoir where the water was able to achieve, the water will displace the oil, but a lot of the oil may be trapped in ganglia. And these ganglia are trapped by capillary pressure. So in order to mobilize a trapped ganglia, you need a pressure difference action on the ganglia that's able to overcome the capillary pressure that keeps it in place. So you have this more or less stability criteria that the water, the pressure difference in the water phase needs to be higher than this capillary pressure. So in order to mobilize oil ganglia, you can reduce the capillary pressure, for example, by lowering the interfacial tension between the water and the oil phase, or you can increase the water pressure drop acting on each of the individual ganglia. So here we are going to discuss ways of increasing this pressure drop in the water phase by discussing a nonlinear physical phenomena by adding different agencies or different components in this water phase. In order to study this pore scale flow, we use visualization. I'm going to show here two types of visualization that we use. The first one is a two-dimensional visualization. So we use a model porous media in two-dimensional, which is made out of a regular network of constricted capillaries. So you have capillaries of different sizes, and these are randomly distributed over the network. So you have capillaries that they don't have any constriction. They have 110 micrometer diameter. And you have capillaries that have constrictions of around 80 and around 60 micrometers. So since they are randomly distributed, you give some heterogeneity of the porous media. These micro models are made out of glass. So which is, you get improved visualization because you have very clear optical access. It's easier to control surface properties. So we can make them water wet or oil wet. We recently published a work on this. And also you're able to achieve higher pressure because the bonding between the glass plates is very strong. So this is a typical experimental setup of these two-dimensional visualization. You have syringe pumps that pump the different fluids. We put these models on an inverted microscope so we can get image and then we can process this image. So this is just an example of these types of visualization. Here's a pore scale visualization. The water is dyed with this red color and the oil is transparent. So this first video is a microscopic flow. You can clearly see the unstable displacement front because you're displacing a higher viscosity oil, which is in this case has a viscosity close to 18 centipoints by water. And here was just a pore scale visualization. And again, we can clearly see the trapped oil ganglia that's surrounded by the water phase. So this, you need a higher pressure in order to displace these ganglia. So as I mentioned, once we get clear images of these devices, we can use image processing to actually measure how much of the space is occupied by one phase or the other. So here's just an example of what happens if we increase the flow rate or the capillary number of the flow. Starting from a very low capillary number, you leave a lot of oil behind. And as you increase the capillary number, this is well known, the amount of oil that remains in the porous media drops considerably. So here you go from a remaining oil saturation of close to 50% to down to 16% by increasing the capillary number. And the other type of experiments we are using is 3D visualization of the porous media using confocal microscope. So confocal microscope has the advantage that you can get very clear image in the focal plane, and then using this concept of pinhole, you can basically filter all the out of focus image. So we are using glass bead packing as our model porous media. And then we need to use fluids that have the same refractive index of this glass sphere, so you don't get the refractive of the light as it goes through the porous media. So the way confocal microscope works, you're gonna make slices, getting images, clear images on the focal plane. And then once you get all these sliced image, you can random them and get a three-dimensional visualization of your specimen. We use these different fluorescent lights, fluorescent dyes on the different phases, such that we can visualize both phases simultaneously. So in this example here, in this picture I'm showing, water is shown as this blue phase and oil is this yellow phase. So with this type of technique, we are able to see transient events. And again, we are watching here a cube of more or less 500 micrometer by 500 micrometer. And you see the oil, which is again indicated in yellow, is displaced by the water phase. And then you can get very detailed description of this transient process of this, in this case, is this drainage of the oil that wets the porous media. And once you reach steady state, you can get very detailed information of the trapped ganglia. And then you can really get a very, very detailed description of what went on. So the first example I'm going to show here is associated with the viscoelastic flow in porous media. So this was the work was done by Nicole Lima, who is a PhD student, and Jorge Avendano, who is a research fellow in the lab. So we can model pore throats as a capillary with a constriction. And as a high molecular weight polymer solution flows through this constriction, the molecule will get extended in this converging diverging channel. If you have a viscoelastic liquid that has an extensional thickening behavior that's associated with the resistance to the straining of these polymer molecules, you depart from this linear behavior between the pressure drop and the flow rate. So for example here, if the flow rate is small enough, such that these viscoelastic forces are not strong enough, you follow the linear relationship of pressure drop and flow rate. But as you increase the flow rate, you get a higher and higher extension rate. So the extensional viscosity starts to becoming more and more important. And then you start seeing this extensional thickening behavior that shows up as an extra pressure that you have in these flows. And what we wanted to understand is if this extra pressure that you see in a single pore throat is able to mobilize oil ganglia that are trapped by capillarity. So we use as an oil phase this mineral oil with a viscosity of close to 18 centipoise. We displace this mineral oil by water, by a polymer solution, a PEO solution with a high molecular weight and a concentration of 0.1%. The shear viscosity of this solution is close to 80 centipoise. It has very mild shear thinning. And then we use a glycerin water solution that had the same shear viscosity of this PEO solution. So the idea was to isolate the viscoelastic effect. The glycerin solution is a Newtonian solution, but with a higher viscosity and with a viscosity similar to the polymer solution. So this polymer solution, we measure the shear viscosity in a rotational rheometer, and also using the Caber instrument, we got an apparent extensional viscosity of this fluid, and you can clearly see the extensional thickening behavior. As the extensional rate increases, you get almost a 1 order of magnitude increase in this apparent extensional viscosity. So we do the experiment, we saturate that two-dimensional porous media with oil, and then we displace by these different aqueous phases. So what I'm showing here is an image of a part of the porous media after the reaching steady state, after the displacement of water, which is shown here in red, of a glycerin solution, which is in this middle image, and the PEO solution, which is in the right image. And then we show this for 3 different flow rates: a very low flow rate, an intermediate flow rate, and a high flow rate. At the very low flow rate, you see the remaining oil saturation after the water displacement is around 38%, and that of the glycerin and PO solution is around 30%. So it's slower than the water solution as expected because oil is being displaced by a higher viscosity aqueous phase. But the remaining oil saturation of the glycerin and the PO solution is basically the same. So that tells us that this process is being dominated by viscous force. So the extensional viscosity is not important at this low flow rate. It remains not being important at this intermediate flow rate. Again, as we increase the flow rate, the capillary number goes up. And then the remaining oil saturation drops. So it goes from 30% to close to 25%. But again, the glycerin, the PO, remaining oil saturation is still the same. And as we increase the capillary number even more, now you can clearly see a difference in the residual oil saturation comparing the glycerin and the PO solution. With the glycerin, you get a 22% oil saturation. With the PO, a 15% oil saturation. It's important to realize that as we increase the flow rate, we are increasing not only the capillary number, but also the Weissenberg number. So the elastic forces are becoming more and more important. And then that's when you start seeing the difference between the glycerin displacement and the PO displacement. So we can map these results in an oil saturation as a function of capillary number. The blue circles are for the water. The red crosses are for the glycerin. It's lower than the water because, again, it's just a Newtonian liquid with a higher viscosity. So the viscosity ratio between the phases is different. But now what's interesting is looking at this PO solution. At low enough capillary number, the remaining oil saturation of the PO and the glycerin solutions are the same. But above a certain flow rate, above a certain Weissenberg number or capillary number, you see this dramatic drop on the remaining oil saturation. That's associated with these viscoelastic forces. We can clearly see that the size of the trapped ganglia at that higher flow rate really changes a lot as we go from the water phase to the glycerin. You see, in the glycerin solution, you don't see these really large trapped oil ganglia. But then when you compare the glycerin solution with the PO solution, you see that the size of the oil ganglia that remain trapped with the PO solutions are much smaller than what you observe with the glycerin solution. Again, the viscoelastic forces were strong enough that led to higher pressure gradient acting in each of these individual oil ganglia, and then we were able to mobilize these oil ganglia. So this was an example using the 2D visualization, and I'm changing the story here now for a flow of suspension of soft capsules. This is a work that's been doing a lot of people involved. Rafael finished his master's thesis on that. Bruna is developing her PhD thesis, and part of her thesis is associated with this work. And then Mariano and Deborah were research fellows in the lab during the time that this work was being done. So the basic idea is that if you have a region of a reservoir that's saturated with oil, if you inject water, the water will displace that oil. But again, as we discussed before, some oil ganglia will be trapped by capillarity. So now if in this water phase, we inject some soft microcapsule, if we have the right size of the capsule and the right mechanical property, it may get stuck in a pore throat. And once it blocks that water preferential path, the pressure will go up. So you change the pressure distribution that's acting in the oil ganglia, and then you're able to displace that oil ganglia. So once you displace that oil ganglia, it means that you're increasing the amount of oil that's being displaced. So you need to control the degree of blocking by controlling the size of the capsules and also the mechanical property of the capsule. It's associated how much pressure you need before these capsules can flow through a given constriction. So in order to get this detailed control, we produce microcapsules using capillary devices. So we make these capsules from a double emulsion template. So in this video, you see we have 3 phases flowing at the same time. If you have the right operating condition, right viscosity ratio and flow rate ratio, you get into this dripping regime. The middle phase is a polymeric phase that will cross-link with time or with temperature, depending on the type of system that you're using. So you can obtain very monodispersed capsules, as I'm showing here. The capsules that we are producing are a little bit higher than 100 micrometers. And so we can control the mechanical properties of the shell by controlling what polymer system we are using, the thickness of the shell, because as these capsules are going to deform, you need to bend the shell of the capsules, and bending moment is associated, it's a function of the cubic power of the thickness, and also the degree of cross-linking of the polymer. So we show here in a recent publication the ability to change the diameter of the capsule. So in this example, we are, by just changing the flow rates of the 3 different phases, we are able to go from 260 to 130 micrometer capsules. And also by the same way, we can control the thickness of the shells. So we are able to control both the size and the thickness. And then with the polymer system that we are using, we are able to control the degree of cross-linking. So we can make very soft shells or very hard shells. So we can flow them through a constricted capillary. So here's an example. You have a capsule that's coming to a constriction. Once it gets stuck there, in this experiment, we were keeping the flow rate the same. So the pressure will go up until it's high enough that it will deform the capsule to flow through the constriction, and then the pressure drop will go down again. So the maximum pressure that you need to be able to make this capsule flow through the constriction is a function of the mechanical properties of the constriction. And then that's exactly the degree of pore blocking that you get from that suspension. So here's an example with PDMS capsules. I'm just showing here by controlling the shell thickness here represented by delta and the degree of cross-linking here, we can make very soft capsules that you don't need a very high pressure difference to make them flow through constrictions, or you need, we can make very rigid capsules and we need a very high pressure difference in order to make that capsule flow. So we have this ability to tune the mechanical property to get the degree of blockage that we want. And then we test these capsules in a flow in porous media. And then we are using confocal microscopes to visualize this process. So we start saturating the device, this glass packing, with water phase. Then we displace the water phase by an oil until we reach the irreducible water saturation. In this case, the water saturation was around 16% and the oil saturation around 84%. So what you're seeing in this confocal image is, again, yellow is the oil phase. So you can see that the porous media is almost fully saturated with the oil phase. And then you just have the ganglia, the water ganglia, that's immobile because you're in the reducible water saturation. We use for aqueous and oil phases these fluids that I'm showing here. And the tricky part is to get the right refractive index, because you need to match the refractive index of the glass beads in order to be able to get a good confocal imaging. So in this case, our aqueous phase had a viscosity of 33 centipoise, and the oil phase has a viscosity of 750 centipoise. So you see that we have a very large viscosity ratio between the two phases. And so the aqueous phase is much less viscous than the oil phase, which would lead to a non-uniform displacement. So we inject the aqueous phase at a certain velocity that gives a capillary number of around 10 to the minus 4. And then we are able to displace a lot of the oil, but the residual oil saturation was around 33%. And you can see these yellow ganglia, these are oil ganglia that are trapped. And then we inject a suspension of capsules and then re-inject water. The capsules here are shown in this pink color. So again, we use a third fluorescent dye to be able to see all the different phases. And at the end of the process, you see that the remaining oil saturation went down from 33 to 26%. So we were able to mobilize oil ganglia that were trapped. And also a large evidence that that oil was displaced is that at the end of the water injection, we reach a steady state. And at the outflow tube, you could only see water coming out. Once we inject the capsule suspension and go back injecting water, you see this large volume of oil being flowing out from the outflow tubing. So this was the amount of the displaced oil after the injection of these capsules. So the visualization, the confocal visualization allow us to get a very detailed information of the phase distribution inside the porous media. So it's very important to do this detailed analysis to try to understand all the physical mechanism. So there's a lot of challenges to be fulfilled. So we need to test that in real rocks where the pore size are much smaller. So we need to make smaller capsules and also in large volumes. So we are using the same techniques with other problems. One is a PhD thesis of Paula Hayes. We are working on studying and understanding condensate gas flow. So we are using both capillary network model to try to see the condensation of the gas as you go through the dew point and block the pore throats, try to understand that with the capillary network model, and also pore scale visualization of this process, and also with foam formation. So we are injecting, we have a surfactant solution saturating the porous media. We inject a gas phase, and we study this lamella formation and emulsion and foam formation. So with that, I would like to thank your attention. Thank the sponsors of the oil reservoir engineering and porous media flow of our group. And once this pandemic crisis ends, I hope you have a chance to go back traveling. And if you have a chance to go to Rio, I would like to welcome you to visit us at PUC in Rio de Janeiro. Thank you very much for your attention.